We may as well start. Welcome, everybody. For those of you who don't know me, my name is Stephen Millard. I'm the Deputy Director for Macroeconomic Modelling and Forecasting here at NISA. It is my very great pleasure to introduce this year's Deane-Stone Lecture. Now, this lecture was established to commemorate the work that Sir Richard Stone and Professor Phyllis Deane undertook during the 1940s into the development of national income accounting systems of measurement. And a lot of that work was carried out I'm not sure it was in this precise building, but it was at NISA. And indeed, much of the work was published jointly by NISA and the Department of Applied Economics in Cambridge. Professor Deane later left NISA to join the Colonial Office, where she remained until 1949. She was a former president of the Royal Economic Society between 1980 and 82, and professor of economic history at the University of Cambridge. Sir Richard Stone was awarded the Nobel Prize in Economics in 1984 for his work. Previous speakers at this prestigious lecture series include Professor Sir Ian Diamond and Stian Westlake, we had last year. This year, though, we are very, very fortunate to have Professor Hashem Pesaran. Professor Pesaran is the John Elliott Distinguished Chair in Economics and Professor of Economics at the University of Southern California and Director of the Center of Applied Financial Economics. He is also an Emeritus Professor of Economics at Cambridge University, a lifetime Fellow of Trinity College, Cambridge, a Fellow of the British Academy and the Econometrics Society and the Journal of Econometrics. He has been awarded honorary doctorates by the Universities of Salford, the University of Goethe in Frankfurt, the University of Maastricht, the University of Economics in Prague. In September 2013, he was named as Thomson Reuters Citation Laureate in Economics, and more recently named by Thomson Reuters as one of the world's most influential scientific minds. He served as a consultant to the United Nations, the World Bank, and the IMF. He's the founding editor of the Journal of Applied Econometrics and a founding board member of the International Association for Applied Econometrics. He has published around 250 articles in academic journals and edited volumes, and 19 books and edited volumes. He received the Royal Economic Society Prize in 1992, the Best Paper Award of Econometric Reviews, 2004-05, the Best Paper Award of the International Journal of Forecasting, 2007, and the Econometric Theory Award in 2008. So as you can tell, an extremely distinguished career, and we're extremely fortunate to have Professor Pesaran with us. I should say, I first met Professor Pesaran a very, very long time ago. He probably won't remember this, but I was a very nervous 18-year-old schoolboy. And I came into Trinity College, Cambridge to do an interview. And it was Professor Pesaran who was interviewing me. And he made a very bad mistake in that he encouraged the college to actually give me an offer. So, so that was one glitch, I think, on an otherwise extremely distinguished career. Today, Professor Pesaran is going to tell us about high-dimensional forecasting and its pitfalls, with an illustration to forecasting UK inflation. Of course, it doesn't need saying that we in NISA spend a lot of our time forecasting, so this talk is highly relevant to us. Professor Pesaran, the floor is yours.
Thank you very much. Listening to the introductions, I feel older than I felt earlier. But nevertheless, thank you very much. And I'm very pleased that I was involved in you going to Trinity. I was very pleased with that. And I also am very especially honored to give Deane-Stone Lecture. I was quite close to Stone, and obviously I knew Professor Deane very well, and I actually did an interview with Professor Stone, which was published in Econometric Theory, 1991. It's a very readable interview. He actually explained his work on national income accounts quite clearly, and how the war effort was involved is important in that, and the role Keynes played in that as well. So it's very much honored to give this lecture in the names of Deane and Stone. Thank you very much for asking me. Now, this work basically summarizes some of the work I have done with many different co-authors, one including Ron Smith, who is sitting behind there. And when we're going to write this paper, we'll be joined with him. So he said he doesn't want his name on the slide. And you know what Ron is like. I always underestimate the huge role he has had in many work I have done. What this paper about, I think I was listening to some reading on BBC, and this jumped up, and I thought that's really relevant. So I thought it's a good idea to insert it. It speaks for itself that one of the problems in our decision making is we need to know what's the other side of the hill. And that's what we're going to think about. How do you go from what you know to what you do not know? That's what Hume also discussed. People don't know how difficult this problem is. And often we pretend it's easier than it is. And I think it's maybe after this talk we can talk about it and get your views on it. So I'm not going to have an introduction. I want to just jump into the problem. I said, suppose that you're asked to forecast a target variable. Now, of course, we may be forecasting many target variables. It really doesn't matter. This argument that you need consistency, the way you forecast all this target, is based on this assumption that they all fit within a particular model. But in practice, that may be actually not a good start in forecasting. You should think of each variable, in my view, separately. Now, I'm not suggesting this approach is for policy analysis or policy making. We come back to that. But I think it's important to do this analysis before you even think of a policy model and policy formulation. Because that puts a boundary, but tells you how much you can learn from the data before you start thinking about a more structure on your data and forecasts. And often we want to forecast more than one step ahead, and that's very important in high dimensional setting. Because when you want to forecast, say, a year ahead, and you have quarterly data, you have 4 quarters ahead. And when I was developed for my automated trading system before anybody started this in a hedge fund, the first thing I learned that is no point just forecasting the market tomorrow, because if you forecast the market tomorrow and other people also get it right, by the time you get up in the morning, the prices are moved away from you. So therefore you don't make any money out of the forecast. So you need to forecast 5 days ahead often. You always need to forecast longer than you think, in my view, but that's make it even more difficult. But then the problem with high dimensional setting, which is the focus of this work as well, is that if I want to do forecast more than one step ahead with a lot of variables, it means that I have to have a gigantic VAR. It's not a G-VAR that some of my students call global VAR, gigantic VAR, which basically links everything together, and that's impossible. So the way you can do multiple asset forecasting is do one variable at a time, especially if you have lots of variables to look at, because you can use what's this approach called direct method, which we're going to discuss. So bear that in mind, especially in inflation targeting and all of that. You really need more than maybe a year and a half, 2 years ahead. And it's very difficult to do a forecast such a long period ahead. But nevertheless, you have to try it. And of course, in practice, you also have a number of variables that you think you should always include in your analysis. For example, if you're forecasting inflation, it would be odd not to put lagged values of inflation in your analysis, because we know inflation is persistent, and the reason it's persistent is because of the wage price, not a spiral necessarily, connection, and also because of the connection of the commodity prices, one contribute the rest of the world, and these are going to cascade very gradually. So therefore, in case of inflation, it's obvious that's what you need to do. So, but if you are predicting exact return, maybe you don't want to do that as such. So these variables we call Z variables, like the intercept or lagged values of the variable that you are going to analyze. Now, as I said, because you want to do multiple ahead forecast, you need to do direct forecasting as opposed to iterated. If you have a VAR, if you have a model which is complete, you can forecast tomorrow, use your forecast of tomorrow to forecast the day after tomorrow, and iterate forward to any time you want. But you need a complete system to do the iterated forecasting. You need complete. It means you need to develop a model for all the variables that you're considering. Now, you can do it if your time of Sims, who got a Nobel Prize for it, you've got 6 variables. Maybe you could do it. Even that, I think, is too many. 6 too many, maybe 3 or 4 variables. Those of you who work with these models. So basically, as soon as you go with a large number of variables, you cannot do iterated forecast. So the only thing you can do is to do direct forecast. What does it mean? It means if I want to forecast 5 days ahead, I move my data today. If I'm running a regression, I have to run the regression today against 5 days ago. So you have to put 5-day lags for everything, so that you are able to forecast 5 days ahead. But as you lag more and more away from where you are, there's less persistence in the board, and there are less variables you can actually pick up as a predictor to forecast. So in other words, if you were doing 1 step ahead, you may get a lot of variables significant, or making important for your analysis. But as you want to go 4 quarters ahead or 2 years ahead, you find very few variables left in your analysis. So that's very important thing to bear in mind. Now, of course, you may say, why bother with a large number of variables? Because we think these large number of variables have commonality, which you're going to come to, which helps you to fill some of the gaps in the model that you would do if you just use only a few variables. For example, suppose you only looked at inflation, unemployment, and output growth. You lose foreign variables. You lose what's happening in the labor market, what's happening in supply chain, what's happening in all sorts of other areas which are connected to the inflation which you left out. But as soon as you start bringing those, you cannot do a complete system, right? So that hopefully everybody agrees with that. You just can't do it. Now, so basically, if we start with it, so effectively what we're saying, we have 2 sets of variables at the moment. We have a set of variables Z, which we like lagged values or intercept or seasonality or something like that, which we always want to keep in our model. The problem is that we have this large number of variables X. This X is high dimensional. Z is very low dimension, is a few variables, which, as I said, 1 or 2 variables maybe. X could have a dimension which is very large, and the problem you're facing is to forecasting YT plus H, which H could be, say, 4, using the data, which is X and Z. Here, I'm not lagging things. I am saying you're forecasting H period ahead, so you can use any data you have now, anything which is available now. It's easier to understand. But you want to run a regression, you have to lag everything, right? So that's just for the sake of argument. And we all know that in mean square error sense, the forecast is optimal if you just calculate a projection on all of the data that you have at the time t where you observe the world, whatever you observe. Of course, doesn't mean you may be at time t, but you don't observe the world. Like data is lagged, unemployment delays. Basically, everything has to be available at the time that you are forecasting. So when you look at this problem, we're going to use this thing which is become popular in a jargons that a lot of people use. We're going to talk about nouns. What are known nouns and known unknowns? And that's very important in forecasting. Now, it is so I'm trying to formalize this idea. So what do we mean by that? For example, if I say I've got a lot of variables, right? If I don't say any more about this, it doesn't help me how to use this variable to forecast tomorrow. But if I say I have a lot of variables, 1,000 variables that I can choose from, and a subset of them, a few of them, like say 2 or 3 of them, they actually are the causal for the variable I'm forecasting, for the Y. This is what you may call known knowns. Because although I don't know what variables enter my forecasting model, but I know it belongs to a set, right? That I know that much. And most of the machine learning literature, and most of the high dimensional literature make this assumption. Because otherwise you cannot have any theory proofs, right? If I say to you that I have lots of variables, 1,000 of the variables, and some of the variables which are help me to forecast Y is among them, but there are some other variables which I don't think are among those variables. You cannot prove anything, because those variables that you think control Y, but it's not among the set you look at, you can't find it because you admit that they are not in the set over which you search. I remember my children would come and tell me, look, they can't find something. You go to the room, it's a mess. The first thing you tell them, clear the room, then you find it. The question is, which side of the room do you clean? If the thing you are lost on this side of the room, and you do a very good search this side of the room, you're not going to find it. It could be really great search. So therefore, the theory of, if you like, statistics and machine learning, all of them have these fundamental assumptions that there are lots of variables, but the word which I don't know belongs to that set. Right? Bear that in mind. All of the results, lasso, method I have developed, all of them is subject to this deficiency. Okay, so there's always a possibility that even if we do the best we can, still we get it wrong. Okay, you have to know that. Okay, so we call these known knowns. Still, it's difficult because if I have 1,000 variables and only 3 of them are relevant, how do I find these 3 variables? The interesting is, the good news is you can. It looks, in fact, the more variables you have, the easier it is to do it. It'll be sort of surprising to a lot of people, but when I explain it, maybe it becomes clearer. So we come back to that.
Can I ask a question?
Of course. Sure.
You said you're not quite sure which variables to choose. Am I right in inferring that you have developed or you're not using some particular aspect of economic theory which determines the choice?
No. Remember, I had a variable Z in this context, Z, right? Remember, I said there are variables Z and X. The Z could be the variables that you really think economic theory tell you and you want to definitely keep it. I'm not ruling that out. Now, the set of X are those variables that you think they could help you, but you don't know which one. Okay, that's a large number of them. That's why when I was a student, we didn't think of that problem, right? We only thought about the small number of variables from which we selected the model, right? But now we know that there are lots of variables in the world that could affect the process we are looking at. So the idea here is that select from those sets. The point I'm making now is another complication. In fact, there may be a variable which affects the target Y, which is not in the Z, is not in the X. It can happen like COVID. Before COVID happened, it's a good example, COVID. Nobody knew it belonged to any set. Do you agree? That's why we were totally at loss. So the fact that we say, oh, it doesn't happen, I think is when you get what I call cold comfort, right? You tell yourself, these things don't happen. This thing, the probability measure of 0. But one of the things I've learned, I think that's a mistake. You should always allow for it. No, not at all. I welcome it. Those people, my students, are always welcome because then it allows me to focus on what I think is interests people. Thanks so much for asking the question. So let's just talk about the problem of case of known knowns. Look at, suppose YT plus H, think of inflation. For UK inflation, Y, we want to forecast it H period ahead. That's my target. The Z, going back to your point, are the variables you favor. You want to include in your model no matter what. As I said, I would put lag values of inflation, right? Because I know inflation persistent, I would definitely put them in. So I don't search for it. I don't leave it to chance. I always leave it in, the Z. But then I have got K variables. These are, K is very large. That's the point. And that's why you need to have this method to do forecasting HSF ahead. You can't go and iterate because K is very large. So this is the idea of that there is some other variables apart from the Z that you have chosen, which could affect Y, but we don't know what they are. But you know they belong to a set. That's why we call it known knowns. It belongs to a known set. This problem is solvable. You can solve it. And that's what happened the last 15 years. Now, there are many ways you can solve this problem. One is, some of you already know, lasso. Some other people have suggested other methods. Usually, what you do, you penalize the model so that the more variable you select, the more costly it is for you. And that's a trade-off between the cost of adding variables and the benefit that that variable may give you. And usually you can find by cross-validation, statisticians love cross-validation, you can solve the problem. I mean, usually it's written like this: you minimize the error of you make for the variables you select. That's the forecasting error, for example, averaged over a number of years, number of quarters, and then you penalize it. And the key often is, what parameter do I use to penalize? Typically, what people do, they for selection, they set gamma equal to 1, they put alpha equal to 0, and that's become lasso, and they only select lambda. I don't want to get into the statistical issue, how best to select lambda. And there are some typical problems is in computer jargon that you try different ways of selecting it. People use nowadays called tenfold cross-validation. And basically what they do, they split, suppose you've got twofold cross-validation, you split the sample that you have. Suppose you have got 100 years of data, for example, or 100 quarters of data, you split it into 2 halves, you estimate the model on 1 half, you predict on the 2nd half. And then you evaluate the model based on the 2nd half. Now, people say 2 is not enough, we do 3, you do 4, you do 5, you split the data into 10 components. In a statistical literature and machine learning, you have lots of data. They often think that doesn't matter, you can always do it. And often the data is random. They have from individuals or firms, they are more typical random, but when you can apply this method to time series model or macro models, they often don't work as well. Because the world that we live is not random. So you can't, when you do cross-validation, how do you split the time, the UK history into which bit? It's not random. So basically that's a problem. So I don't want to go because there's so many things to cover. So basically these methods are referred to as penalized regression, which is obvious. Like you have a regression that you have got to this side and then you penalize it. Now, one of the interesting things about this that you can avoid this. So I spent a lot of time thinking about this problem. So we finally, published a paper in Econometrica with George Capitanos, who is my student, who is in King's College, and one of other students from Cambridge again, Alex Chudik, where we came up with this idea that you don't really need to use penalized regression. You can. So therefore, you don't need to cross-validate, and therefore, you don't need to worry about the dependence of the data, and you can apply this to economic data much more readily. So the idea is so simple, but to prove it is not that simple. Let me tell you the basic idea. It says one covariate at a time. Remember, we go back to our regression. Let's go back to this regression. So that's what we have. We already know what the Z there in the model, but we have 1,000 variables. We don't know which one to put in. There's no point running a regression with all the 1,000. That's why you penalize, right? So that's why you penalize it. The idea what we developed, which is OCMT, which is called one variable at a time, multiple testing. Now, the idea is the following. You say, okay, I've got 1,000 variables. But what matters, if any of these variables were important, would have a non-zero correlation with Y. There are cases happen that you may not get that, but it's very rare. So why don't we try one variable at a time? In other words, we run, if you have k covariates, k variables to choose from, you run k separate regression. Each of them have single additional variable. one at a time. It's very fast, right? Doesn't have cross-validation, it's very fast. But then you may say, well, of course, if you time 1,000 regression, a lot of them get significant, that you're making a mistake. So to deal with that, what we do, we jack up the critical value. So in other words, as you have more and more variables, you require the variables to become more and more significant. We have a formula how you do it. I don't want to go into that. So the idea is that effectively you throw all the noise variables almost immediately. You know, imagine out of 1,000 variables you have, 900 of them are totally useless. Somebody told you put it in, totally useless. What happens if you run a regression of Y on that totally useless variable? You get nothing, especially if you have the critical value, not your 2. You remember when you do a t-test, use 1.96, don't use 1.96, use 3. So the variable has to be strong enough to pass the bar. And those of you know, when you use the critical value of 3, it's very rare that something gets selected which doesn't belong to the set. It's almost very unlikely. We don't use 3, we use 2.75 or something like that, depending on the number of variables you have. As you have more and more variables, we jack up the critical value. That then controls the selection. And it works so well. I mean, not because we developed it, everybody does it. You know, one of the things, I've got another student I'm talking about who's now in Pittsburgh. He has got a paper in Journal of Econometrics. The referee's complaining that he doesn't show any method that beats his method in forecasting. So he's asked, the question I've asked him, go and find a way that another method you find that does better than you. So basically, in other words, argument is that because you don't do cross-validation, and because when you do lasso, you really need to have independence also uncorrelated. Of course, this method would not work if all of these variables, all of the x's you have, they were all tied up to one fundamental factor, what we call a factor model. Imagine there is a one overriding factor, again, COVID, affected everything. So everything becomes correlated with the Y. And this method I just told you breaks down. So what is the solution? That's why this student solved this problem. His name is Iranian, as it happens, and his name is Mahdad Sharif Waghifi. I'll come to it. So what you could do, you could then say there's a factor which affects everything. If this factor affects all of the variables, it means every variable gets selected and is going to break down. We come back to that. So what he did, he basically said, the idea is very simple. If there is a commonality among all the covariates I am selecting from, why don't we subtract this commonality, which we call principal component, right? You then run a regression of the target variable Y on the principal component, then look one variable at a time. So basically, you separate the commonality. So you take away, you filter out the correlation, which is across. So the way to think about it again is that if there is something which is central to every variable that you're analyzing, filter that out. So what is left become uncorrelated with each other. And therefore, you can apply the method. So you can solve the problem even if you have very highly correlated set of variables. Again, lasso cannot handle it, because lasso requires reasonably independent variables across the thing. So we have solved, in my view, the problem of selecting from a large set, so long as the variables that you're selecting is relevant to the target variable you're analyzing. So you're not leaving anything out. Now, as I said, you don't have to take my word for it at the moment. We can talk about the literature. And so I'm saying we can solve, this problem is solved, in my opinion. So this is basically, and there is lots of results for it. So that's what we call, when you are selecting a variable with very highly correlated covariates. This is a very difficult problem. The reason it's difficult is obvious, because if all these covariates very highly correlate with each other, how can you tell the difference between them? You can't tell the difference, because if they are highly correlated with each other, which basically means if one of them helps you to forecast Y, it means another one would look like it's helping you to forecast Y. But that doesn't mean all of them are relevant. That's the problem with macroeconomic issues, because everything becomes correlated. So as I said, the answer is actually using principal component. People have used principal component, but they haven't used the additional selection of the variables. For example, a lot of people have worked on this model, a factor principal component problem. They are only interested in the factor and they think this factor affects the y. But in practice, it may be that actually there are variables which sharing the factor which affect the y, not that the factor f affects the y directly.
So the final forecasting model is all the x's that are significant of 3 plus the f plus the z.
Yeah, you could, yes, that's right. That's right. So basically, what is saying that, of course, f may not belong to the, because if the f affect the y indirectly through x, you may not have f at all in the model. But you are right. The Montcalli has done suggests that even in that situation, putting f is still better than not putting it, right? Because imagine you left one of the variables which were important, but by putting the f in, you cover some of the fact that you left something out. So therefore, the answer is very simple. You don't do just principal component analysis, right? You run a regression of y on principal components and the variable you select one at a time. And that's it. So it basically marries the two sides of a literature. So it's very straightforward to do, by the way. I mean, I'm just saying, although mathematics of it is a bit heavy, but the actual understanding it is very straightforward. Okay, now let's look at this is the situation. This is it. You see, you don't have f in there at all, right? Because imagine x is all of these x's are affected by the f, right? So therefore, if you select the right x, you don't have any f in here. But it's possible that actually the model is more complicated than this. Not only f affects y through x, COVID affects y through the variables, right? Because COVID affects our behavior. Our behavior, which are x, affects y, which is inflation, output, growth, and employment, right? But it's possible that the COVID also directly affects y. So you need to allow for that. That we call it known unknowns, right? So basically, it's not true necessarily that everything goes through x, the variable you have selected. It could be some other factor which directly affect y. That's new. That's what I'm going to tell you now. Okay. So what does it mean now? The answer is the following. So by the way, this is what we already discussed. The way you solve the problem of very correlated variables, you put the factors in, and these are the filters effect of the factor, and that's why it works. Okay. But as I said, that doesn't mean the factor is in there. You put f because it was a part of the x. Now, let's just now go and one step further. So anyway, these are the details of why it works. I mean, some of you may want to be interested to know, when you do one at a time, you use the critical value, and the critical value is basically related to this number of covariates you have k. If k is 100, your delta is usually 1. If k is 100, you divide your 5% divided by 200. So the p becomes very small, effective p. If k is 1,000, the critical value becomes even higher. But remember, when you have a Gaussian distribution, you don't get above 4. How many times any of you have seen draw a random variable which is get larger than 4? Very few times, because of the distributions relative. So basically, let me just move on. Let's go into the details of that. So basically, it's possible that you could have a factor also in the model. In other words, this is the model that people use. You could be factor in the model, no x's. But in practice, it's very rare that you have that. That's the model that in America, a lot of people use. Now, what happens now, if you now have the z you have selected, the set of 1,000 covariates from which you need to select, but also there are unobserved factors which you don't know. These are the ones you don't know, okay? So these are basically known unknowns. In other words, I know that I don't know what f is. Now, can I do anything about that, right? It seems a bit, of course, I have to have a structure. I have to say where this f coming from. Notice here that, imagine, I'm looking at the UK. and that's UK inflation. The lag, I put the lag value of inflation here. I looked at all the variables the bank has and searched over them, and I find a few of the variables there. But I say, but there may be something missing. F. Can I do anything? Now, if this F was the one which was common across X, yes, you could take the principal component of X and put it here. But F need not belong to the X. F could be outside the UK. International community, the global system, right? So what does it mean? The answer is you need to use a panel. In other words, you have to use other countries in order to look at the UK, right? You need other information, right? Yes, please.
Second order question, but like, do you discipline the dependence of the phi, the bold phi on H? I mean, in the world I live in, I would imagine that if I'm only changing my horizon from 3 to 4, say, I should expect in some sense the same selected variables, the same. Do you discipline that? I mean, do you? No,
you can't.
That,
no,
I leave it free.
Basically, leave it free. I mean, it's just if you want to answer that question, you have to have the gigantic one.
Yeah, exactly. Well, you have a smaller model, but you have.
No, you can't. You think about it because you don't know what the selected, right? You don't know what you have 1,000 variables.
So everything you showed so far is based on a single H. I'm just saying, like, is there a connection between your estimates?
No, there is, but for that I need X and Y together and model everything together. How would I know what?
I would just say take a really simple thing, like I would penalize it if I was selecting different X's for 3/4 forecast horizon. For
yeah.
4 horizon.
I mean, this is you make assumption, but the question is if you want to say the rate. For example, when you have an AR1, right, one order, the AR coefficient basically rho to power of H become the way it declines.
True, that would be a very, very strong.
No, but that's
yeah. Slightly, still yeah. Maybe not quite allow.
No, I mean this is you could do it, but I'm just saying usually in this what's called direct forecasting, people don't do it.
Yeah. I understand they're getting away from the AR. Yeah, exactly.
Yeah. Especially when you have high dimensional systems, it's very difficult to know what to do. But I mean, this is an open question. I'm not suggesting that I know the answer. I remember when I was doing H1, we used to have a model, Monday model, Tuesday model, Wednesday model, Thursday model, Friday model. And the question was, people asked, which model do we use? We looked at the difference. It didn't that much difference, to be honest with you. So basically, yeah.
So you mentioned natural variables as like getting FT. Why wouldn't you just include them into the universe case?
You know what? Include them
into the case of the variables. So you said we have these variables outside of the UK. Why?
No, I'm just saying if it was. I said maybe I did explain. If F belonged to the set X, we use the factor domestically in the UK, and you're done. But what if it was outside UK?
So I guess what I'm saying, if you approach it from a pure machine learning perspective, just stick in the
you'll see in a minute. It won't work.
Okay.
It won't work. The reason is that
economic discussion poll questions, and so.
Let me just. Yeah. Okay. So I'm running out of time. So let's just see in a minute. You'll see, right? So basically, this is a model that the UK has, but I'm just saying, F actually is affecting Y, but it doesn't come from the domestic variables. That's the only thing I'm saying. You may say that, it should come from the domestic variables, but I'm going to argue that that's not the case. Remember, it's forecasting. Again, if you look at the COVID, you'll see. Why would the COVID effect be among the X's that UK observed? But imagine COVID happened in China before UK. Another example I have with this is California. When the flu season starts, it starts from Northern California because they called it earlier. So therefore, if I see what's happening in Northern California, I may learn more about what may happen in Southern California. So it cannot be within the Southern California data. So a spatial dependence could be one reason for this. What they call ripple effect in regional science. Economists don't use this idea. They should. Okay. So basically, let me just go very quickly. Now, in order to then address the question a bit more broadly, which is related to what you're asking, I'm going to introduce an I here as well. I is a country, okay, or region, or industry, doesn't really matter. At the moment, because we talk about UK inflation, think of countries. Country I would have n of them. So n is large as well now. You have a large number of countries. Large doesn't mean 200. 30 is large in this literature. And because of the countries are not that correlated very much after you condition on these variables. So basically now you have, each country has got their own pet variables, let's call them, the variable they love to include, they include it here. They have large number of variables from which to search from, which we do one at a time at the moment. But then they have their own factor, but there's a global factor as well. So there are two types of factors. One domestic factor, which is common across the economy, across the, for I, but there is something which is common in the world economy. Like, for example, a dramatic climatic change happened in the world, right? Which affect countries differently. It doesn't mean it should be the same because it's epsi IH, right? So that could differ across countries. For example, some phenomenon happens somewhere in the world, doesn't affect you, but doesn't mean that's not there. Okay. So in order to solve this problem, you need to have a hierarchical model. The hierarchical model says that the domestic factor affects all the excess domestically, right? So that's one. But the global factor affects all of the factors across the countries. So that's why you need both the structure. And the reason why it's also helpful is because it allows you the ripple effect that I explained a minute earlier, right? So then the question is, how do you solve this problem? I've actually asked one of, Mardot to look into that. We write another paper, we have to write another paper, but the logic is actually turns out the same as what we have already done. You basically, you extract a principal component of the X to give you identify F. You then extract a principal component of what? Of the Y. So what is the principal component of the inflation? Is world inflation, if you think about it. So basically telling you that in order to model the inflation UK, you need to always consider the possibility of world inflation or inflation which is more relevant to UK, the rest of the world. So it's very simple. So this is the basic idea. I'm just running out of time. So let me go to the application. Some of these issues come out very quickly in the application. So basically, to run it by you, we're going to look at inflation in the UK using the same methodology I've developed. So it turns out that actually very few variables we found that affect UK inflation, especially as you go H4, as you go, hardly any. One of the reasons is as you go H4, the persistent also decline. Remember, we also included already the UK lagged inflation, right? And when you put those in, this is very, very little left. So what we end up with, I don't want to go into that, we end up with these are the Z variable, inflation, and that we end up with the foreign inflation and lag. The way we define the foreign inflation is not just simply a global inflation, but is related to UK. So it's a weighted average of all the other countries' inflation, where the weights are trade weights of the UK. For example, if UK trades with Europe, obviously which it does, gets more weight as compared. Yeah. So very quickly, basically that's what, if you see why this is the case, this is the inflation in advanced economies. You see how the spread of this is declining and you're getting much more condensed here. You see, you can't get away from the rest of the world, right? You cannot have, you can have a little bit leeway here and there, but you cannot deviate from the rest of the world that easily. Okay, people want to do it, but you can't, as we are tied up. So basically, this tells you that if you look at what we call UK, this is the UK inflation, the blue one, and the red is the global, what we call global inflation, but this is specific to UK because we use the UK trade weights. You see that it's becoming much more tied up together over time. So we found that, so when we say, okay, we use this model, we forecast with it, one period at a time, we use H4. As I said, we don't combine them together. We could in this example because there are very few variables in the model. In fact, we do iterated forecast here. So basically, if you look at the 1 quarter of the forecast, also we extracted what was the Bank of England forecast. Again, we're just using it as a comparison. The bank, they all admitted it, they under-predicted the forecast here, but then they're actually over-predicting. pretty big way. I was surprised by that. But the model actually, does okay. It's basically, this is the red one is Bank of England. The green one is what we call the simple model that we have. And the blue one is the actual thing. But 1 quarter ahead, you can forecast okay, in my view. We do better than the bank, but doesn't mean anything. It's not that much of a difference. Okay, because they got it wrong here. I don't know why they came up with the 13% forecast. We need to talk about it later on. But if you go 1 year ahead, things are neither do well, right? As we expected. As you go further in the future, and we did also the iterated one, which allows for the fact that different models have to tie it up together. You see, other people found the same. There's a paper by Marcellino, Stock and Watson. We have a paper with Alan Timmerman under Peak. It doesn't make much of a difference. Okay, so what's interesting is that although you do direct separately, the differences are not that much. In this case, unfortunately, both models, whether Bank of England or this simple model, they do almost similarly. Still, we do slightly better than Bank of England, but nothing to write home about. But look at how you are away from the truth. So very difficult to do anything. I don't think anybody could have forecast 1 year ahead. I don't know what you guys did in the National Institute, but I didn't ask. I'm saying nobody could do better than this, in my view. It's almost impossible because you look at the history and that's what you work with. Even because another thing we do here, we go as far back in the data. Bank, we notice, doesn't use long series going back. That's a mistake. We have another paper showing that if you select a regressors, you should use as long a history as you can. In forecasting, pardon?
2020. You do the same analysis going all the way back. You still do the same.
What do you mean? We haven't done any. We just wanted to, for this, I mean, we can do more. We can talk about it. But so I just want to finish. So basically, there are lots of problems with these models. We also, another point we want to raise that in forecasting, knowing a causal variable doesn't necessarily help you. A lot of people fuss about the structural models. The reason is they don't understand. Suppose I know oil prices affect inflation. It's causal. Suppose it's causal. Can I exploit it? The answer is no. Why? Because I cannot predict oil prices. The Bank of England in their report, Ron helped me to look at it. So fuss about that. What is the government going to do with energy subsidies? Right? You can't forecast what the government is going to do exactly with energy subsidies. You can't forecast the energy. So therefore, modeling condition on that doesn't make you to better forecast. So as an example, I've got many examples of this, but I thought one is enough. Look at this example. If you run the same model we have at the current oil prices, you get significant 3.4. It passes the level I was telling you. And it's significant, is the right sign and everything. But when you put lag value, it goes away. Because in order to use this one to forecast, I have to forecast the oil prices. But if I forecast the oil prices, it's like putting the lag value of oil in my original model. It's not going to help you. So having a causal understanding of the world does not make you a better forecaster. I think those people who understand earthquake, they have told us many over and over again. Everybody, geologists I talk to, they fully understand how earthquake happens. Weather forecasters, I've worked in the meteorological world for 6 years for my sin. All of them, they believe they know the model of the climate conditions. They said the only thing we don't know all the data, initial conditions on all the data. You cannot predict a lot of phenomena, although you think is important. So therefore, really you have to use only lag values. You only use, in my view, if you want to forecast each period ahead, use whatever you have now. So to summarize, when you have high dimension, a lot of things we learn, like iterative forecasting, we were talking about it, goes out of the window. You just can't do it. So what you need to do, you need to always think about what are the factors which are specific to this problem, like a UK what are the factors specific to UK, but what other factors which originate outside the UK, for example. And also bear in mind that forecasting is not the same as a structural modeling. I'm not suggesting you shouldn't do structural modeling, by the way. I'm saying that necessarily doesn't help you in forecasting. And that raises a fundamental issue. What is the role of forecasting in policy design? Okay. Should we just abandon this kind of forecast and just forecast and then say what the policy model, or should somehow find a way of introducing the two together? My view is that the second, not the first. So sorry that I took a bit longer, but I think I'm going to leave it at that at the moment.
To be honest, it could have taken longer in the end. I just didn't realize how you were in that talk.
Don't worry, no, I just thought I just open the conversation.
But that's okay. I was going to be probably having a ton of questions now hanging over. So I see one from Jacobs at the front. I've got one in the second row. Thomas. So if we go Thomas in the second row. Can you please, for the benefit of everybody, just tell us who you are,
My name is Tomasz Fladek. I work at T. Rowe Price. I'm a market economist. I've actually been trying to use the OCMT method that you've described for some time now. And one of the questions I had is, in general, how do you deal with parameter instability in that framework?
Good question. We have I didn't cover it today. We have a paper which is sitting with Journal of Econometrics at the moment. And this is the one, oh, we're gone, the screen gone, sorry. So it's basically, you can look at my webpage, Chudik, Pesaran and Sharif Waqifi, which is 2023. What happens? It's this one. So this is an important question. Imagine the world is changing. Now, if the change is purely random, or the change could be more systematic, I think there are very different way of looking at the problem, but the approach is the same. If I'm going to select a variable, what the only measure I should do in the OCMT method, right, is the average effect over time. I learned that from Mandelbrot, the famous physicist, right? I asked him, if you have the data from the beginning of the Roman Empire, beautiful data all the way till now, and somebody asks you to forecast tomorrow, how much of the data you use? He looked at me. He said, all of it, without hesitation. Without hesitation, he said all of it. And that's the correct answer. So in other words, the economist view of the world, that they do peace deal. They say, I want to use post-war data. I want to use post-COVID data. They want to make their life easy because the world is whatever it is. If I have a variable which could be important, it has to be important most of the time over the last 100 years. You agree? Not a variable which was important now, but never before. So therefore, you use all of the data. And that's what we prove, mathematically the case. And we do all the model. That's why they say, can't you find another method which beats it as well? Because Lasso cannot deal with it. Because Lasso does the estimation and selection in one go. Because when you penalize. But having selected the regressor, you should use all of the data. Right? Why? Because suppose I know that these variables are important, but it doesn't mean their effect is the same over time. Yeah, I agree, they are changed. So therefore, I may have to use a different window or downweight observation, do exponential downweighting, and we show this combination of selecting the variables using all of the data, but using downweighting when you forecast with the data, with the variable selected. So there's a selection use. You have to separate it from each other. And that's the paper there, and the proof is there. And what is interesting, and the proof works far better than I imagined, because it said doesn't matter whether the things go like that or whether the things go like that, so long as the average. When I presented this paper last year in Cambridge, one of our clever colleagues, he said, what about if the effect was half during the half of the sample and then become minus half during the rest of the sample? You don't select it, right? But I said to him, that the problem with this way of looking at it is you have to tell me what is going to happen after this. Most of people think of dummy is very simple problem. Dummy is not as simple, because when you say something a dummy, you say it's 1 and drop to 0 forever. Does it go to 0 forever? So that's the problem. So basically, the only way we have is to find the average effect of a variable over time. So when things vary, right?
Fantastic. We'll take the next 2 questions in a row, and then if you can answer them as a set.
I'm Jerry Houghton, Cardiff Met University. I was wondering how far the OCMT process is robust to non-linearities in the equation. I mean, if, for example, you're dealing with a situation where there are relatively few variables that have a direct effect, but there are other sort of state variables that influence how big that effect is. They have no independent effect on the y,
Yes.
but they condition the effect of the x and the x variables. Now, if you've got that, your T3 or whatever it is that you're going through might be throwing out variables that have significant effect through interaction.
You see, if, as I said, the example I gave that is basically like a dummy, right? If the question of the variable is, this is always this issue. Is this variable going to be continue affecting us as well in forecasting, right? So your point about nonlinearity is well taken. In fact, you can, do threshold. For example, we have some approach that you could put a threshold variable among the set and interact it. There's nothing to stop you, because the larger number of these variables you have, the less problem you have because the critical value keep going up and would kick out anything which was noise. And you're left with the one which actually, as you said, had an effect. Now, but you're right, it's not obvious how do you do it in different settings. For example, how you define a threshold. The threshold effects are very important in my view, but I have no general theory for it.
Yeah, I mean, I'm dealing with a situation at the moment where there are very strong interaction effects among the variables.
That's what I'm saying. The way I would do it, I create a threshold variable and interact it. For example, you say, if like imagine physicists know about it and naturally do it. If we didn't have an empirical analysis of water is frozen. So you have when the temperature goes down, it's frozen. Then when we go above, becomes liquid. Then after that becomes steam. As somebody physicist said, that if we didn't live in this world, suppose the temperature in our world was always below 0, could we ever know what would happen to the water? Do you agree? You wouldn't. So unless you observe have experience of a phenomena, you can never know how to model it in the future, unfortunately. So there is this ambiguity in the world we live in, that at the end of the day, no matter what we do, we have to be humble. You have to be humble.
Thank you. Joji Chad, Director of National Institute. Wonderful having you here today. Very important topic, given what's going on here and abroad with inflation. I just wanted to pick your brains on a couple of things. One is, how does any process that you're looking at here deal with the problem that the future is not like the recent past? So I might do a very good job of trying to work out what happened during COVID, but what happened during COVID is not going to help me very much thinking about what's happening over the next couple of years. How do we handle the fact that any historical, I don't use the phrase data mining because that might have a certain value judgment attached to it, which I don't want, but however well we try to match the past to the data, the future will be something very different.
Yeah.
And certain variables will look important because they reflect a particular shock that the economy was being hit by. I think you touched upon that at the end when you talked about structural things. And so I want to try another tack, which is what's really important about structural, is trying to understand the underlying shocks that are hitting the economy. So in this case right now, the tight labour market, a rapid increase in energy and food prices, and an existing or initial stance of monetary policy that was far too loose. Into that mix, you then got this large increase in inflation. So is it possible to combine a narrative that allows us to think about what shocks they are and weigh them more heavily in your forecast to say, look, we've got examples of an oil price shock. We've got examples of a tight labour market. We've got examples where monetary policy was a little bit slow. Let me be kind to those. And I'm going to put that into the model and then project my inflation forward. Is that a way we can iterate further with your
I think you're correct that the future need not be similar to what we have just observed. This is absolutely the problem with the when forecasting goes wrong, is exactly we are in that sort of situation. We can basically, well, put it the other way, you cannot avoid it, the problem, but you can minimize the effect, right? So the way you minimize it, you should accept that you can go wrong all the time, like a trade-off. For example, I was answering the question about if the board is changing, what do I do? The answer is I take longer period. But if I take a longer period, more likely I may go wrong if the world is normal. Yeah, right. Imagine that when people came out of the COVID, they thought they will go back to normal. And they thought it's transitory, they go back to normal. And that's why they got the inflation wrong, right? So that, because they assume, but suppose they assume it's not going back to normal for some reason, but it did stay like normal. So there's always this danger that whichever you err, there is a possibility of error. I think you have to admit that, in my view. So there's nothing you can do. I think it's like one of those phenomena that you take longer period, that would help you to find out the possibility that inflation could be higher than what we thought. But on the other hand, then you go wrong the other way around, that you predict too much. Like a Bank of England, you saw, then they saw they were making mistake. They saw inflation is rising. They overshot it. Most of their error was because, in my view, they overshot it toward the end. They were in error to begin with. They, in terms of the, I'm not saying the timing, but they overdid it in some way. So at the end of the day, I don't think you can use the theory to forecast better, in my view, because the theory is in your rationale of understanding of the world, but your understanding of the world has to be then converted to some measurable effect, right? And then the question is, like I give you an example, we know oil prices, when it goes up, energy prices go up, inflation goes up. But then how do we know what happened to oil price? Which is more difficult to predict, oil prices or inflation? I leave it you guys to answer.
No brainer.
Yeah, oil prices, right? So that's the point. Yeah, that's the point. But
the conditional forecast gives you an excuse for being wrong.
That's probably true. No, I'm not saying you shouldn't do that. So in fact, a lot of people think I'm not against structural modeling at all. You need a structural modeling to do policy analysis, to understand the world we live in, right? There's no doubt about it. The point I'm making here, don't think that using a structural model helps you in forecasting. That's the only thing I'm just saying. I'm not saying always, I'm just saying that I'm giving you an example that you may understand the world, but doesn't help you in forecasting.
I've got a question right over there, and then we'll come back to Reese.
Professor, thank you so much for your presentation. Very inspirational. You briefly touched on almost transdisciplinary forecasting methodologies when you briefly touched on forecasting earthquakes. Are there any other disciplines you take inspiration from as well to merge your forecasting methodologies possibly in the future? That's my question one. And question two, at the end of your presentation, you said so humility or being humble as an economist is a key asset. Can you develop on that, please?
I think the first one, I always benefited greatly by talking to a lot of other people in other disciplines. Being in Trinity College and meeting a lot of very good scientists has been very important to me. In fact, I spent, as I mentioned briefly, 6 years on meteorological board of UK because one of our colleagues in Trinity became the head of the weather forecasting and asked me to join him. And I asked him, why do you want me on the board? Like now the reverse of what you're asking. He said, look, one of the things that Mrs. Thatcher wanted to reform basically Minister of Defense. The meteorological board was a part of Defense, Ministry of Defense. And they wanted to separate it to sell some of the product privately. Like, for example, you forecast for, weather and for traveling and so on. So they want, anyway, so the question was, it's a very important question, was that How do you measure the value of improved forecast? Suppose somebody says, if you spend $100 million to buy bigger computers and collect better data, right? I'll give you a better forecast, right? And still you can ask the question, is it worth it? Is that a little better forecast? Is it better for the society, right? These are very difficult questions to answer. And I actually learned that from them. And you know how they did? It's so difficult to answer this question because if you are forecasting a hurricane, but you are sitting in your room in front of the fire, it has nothing to do with you. But if you are caught in the mountain, it's very, could lose your life if you didn't know the forecast on time. There are many examples of it. So the heterogeneity effect on the society of this forecast. Like getting inflation wrong is not the same for everybody in this room, right? So I think I learned a lot that we need to also think about how the forecasts are interrelated with decision process. So I worked with Clive Granger, late Granger, who was a Nobel Prize. I learned a lot from him as well, because we understood that you need to work on decision theory approach to forecasting. So in other words, you have to ask yourself, not that you're forecasting, but how do you use the forecast? And what is the value of using that forecast for the society as a whole? I don't think you are even near to that question yet to answer. Sometimes you may have got that makes me more humble because I can't answer. You know what I mean? I leave it to that.
So Reese Pedera, King's Business School. I'm really going to ride on Jerry's question, but phrase it a bit differently, because I used to work with Oscar Jordan. So very little in this so far seems to be raising any difficulty in incorporating it into local projections. For example, so local projection people are sometimes to select variables the same ways. They may not get the same clean distributional results that might get the drill econometrics pub or econometric pub. But do you see a tension between a lot of what you're pushing here and the local projection crew, or could you just take a lot of what you're doing here and putting it in the local projections, get the non-linearities and the things that the local projections guys get? I mean, it seems like mechanically you could do a lot of what you're doing.
But I mean, yeah, the answer to your question is that the direct forecasting method was invented before local projection. So I don't need to take them. Sorry. Here I don't want to be humble. I don't think I need to take their approach into account. In fact, what they did, they basically took over the direct forecasting and they call it local projection. It's one example of marketing, right? You just label something, call it local projection. It's my friend. He's in San Diego, in Davis, and the guy who developed Geordie, and I know him very well. So he's a great guy, by the way. But the problem with the local projection is that the model is non-linear. Local projection doesn't have any justification. It doesn't follow. They use it. But
yeah, that's what I mean. You could do it, but I don't think you're going to get any of the results.
Yeah. So therefore, if the world is non-linear, very complicated to answer the question. I don't think local projection is going to help you. Local projection helps you because what you're doing, you write a small model and you iterate. When you iterate, effectively you can iterate forward, right? Any dynamic model, it doesn't have to be linear or non-linear. Any dynamic model you write down, is complete. It has to be complete. That's the key question. When we say complete, it means that all the variables in your model are fit with the dynamic model. That's complete. Now, if you have a complete dynamic model, it means that because it's Markovian, basically means that if you start from any initial state, you can work out any period up to the future, up to the end of the world, right? That's what the logic of the iterative model is. So you can work out yt plus h going to infinity, right? That's what impulse response effectively is, right? When you h going to infinity. So basically, you need a complete system. My point has been that when you have large number of variables that you need to handle, you cannot follow that approach. It's not available. It's not as a matter of, I've got this approach, I'm going to compare it with another one. The comparison that is available when the number of variables are small. And that people have, like Stockton, Watson, and others have looked at local projection. They say, look, if the model is complete and it's a VAR, local projection is inefficient. So basically, we know that because there's paper written. I don't know whether, let me just show you the paper which I think has been discussed in, if I can go back. Am I going the right way? Yeah. So this is a paper which Marcellino, I mentioned that. Where is it? Here we are. So this is where the direct forecast, these two papers discuss with direct forecast, right? So basically, you can show that if you have a complete model, right, you just iterate. Like what physicists do, right? But the problem is whether do you have a complete model in economic systems? Or if you focus or you insist on the model to be complete, you may be leaving out important variables, right? So that's the problem. So that's, I don't think there is an answer to the question. What's the most efficient way of doing it when the world is incomplete? You can't do it.
Hi, I'm Luca Penarola. I'm here.
Oh, okay.
Thank you very much for the talk. I'm an economist at BNP Paribas. I had a question a bit about parameter instability, but so one of the messages that I gathered from your talk is keep it simple, from what I can see. But I was wondering, how do you deal with extreme volatility in the data? So for example, if I have a model for GDP, which includes a lag of GDP, let's say 3 years in the past, I apply it now. 3 years ago, GDP dropped by 9% in Italy, the UK, and stuff like that. It's going to affect my forecast very heavily. So what do you do in that situation? You say that's the best I can do, and that's it?
No. I understand your question. I did more or less answer that, but I will expand on it. It's good. When Bob was asked the question, what do you do with the word unstable? I said you separate the selection from forecasting. What I mean by that, I mean I have got say 100 variables out there. And before I forecast, you have to select which one I use to forecast with. Do you agree with me? So when you want to select, use long series. Because the selection, when you do OCMT, uses the average over the time. Regression is amazing. It averages. And that's the beauty of it, right? So it takes the average. Okay, having selected, or you have whatever you have done, then I'm not suggesting you just use whatever it is and say, I can't do anything. This is why you need some kind of understanding of the world before you forecast, right? That's why, but people in finance, they call it the choice of window. They use 10-year window, 5-year, they don't know, right? Because they know the world is changing in finance all the time. So they use 5-year window, rolling window, 10-year rolling window. Ask them why, they said the other guy's doing it, okay? I try to approach the problem. I've got 5 or 6 papers on it with very good people. And I came to the conclusion, in order to answer your question correctly, I need to know the nature of the way the world is changing. Right? You agree with that, right? The problem is we don't. We don't. And we can't learn from it. Let me explain why. Suppose you have a world in which is going and only one time it change. If the change which happened is very far away from you, doesn't matter. If the change very near you, what happens? You need to know how to allow, because if you use a short window, we wrote a paper on that. You use a short window, suppose you use a very short window, it's inefficient, okay? Maybe unbiased, but it would be high variance, right? So what do? You have to go back further. So basically, it's like exactly trade-off between bias and efficiency. So what you need to do, you need to say, oh yeah, I know that if I go before the breaks, I bias my forecast, but I may do better overall because I get more precise estimate. So that's a trade-off. But that trade-off, you have to decide, I agree. So I'm not suggesting that. And by the way, none of them are simple.
No.
Believe me, what I say looks simple, but none of them are simple.
If only. I had a question at the back. Do you have a question as well?
But there is some gentleman in the back.
One at the back.
Yeah, thank you very much indeed. It's David Owen from Saltmarsh Consultancy. So when you did the inflation equation, were you disappointed that you didn't get more sort of economic variables left at the end of the day? That's one question. The second question is, obviously the bank is setting its forecasts over the 2-3 year rolling horizon. So it doesn't make a particular difference if you roll out the horizon beyond 1 year. So going back to the equation you showed, I think it's
we didn't. We only wanted to use this to. Sorry, answer the last bit of your question before answering the first part. The last bit, the reason I think we did it with Ron, by the way, is just we wanted to focus on the 2 years that Bank of England was focusing, and we can't go 2 years ahead. And that's the reason. But of course, if we wait another 2 years, we could do that, right? We could do. But if we went backward, we do very well because the inflation was flat, right? So we didn't want to show it's doing well because we wanted to know what happens when inflation starts to rise. Okay, so that's the reason we didn't go 2 years ahead. We just stopped 1 year ahead. Ron, am I not correct? Yeah, that's the reason. Not that because we didn't want to do it. It's just.
I mean, they do place emphasis on the 3-year forecast. It's obviously in their spreadsheet, so also you get shocks to extend that time horizon. So.
No, I mean, I think what happens if you go, I can answer you the question. If you do direct method, which we're doing, if you go 3 years, you basically historical mean. You know what I mean? It's just take historical mean, and that's the answer. Right? Because you think about the dynamics of adjustment, it finishes between a year and a half, 2 years, or maybe 2.5 years, right? For 3 years, for sure, in my view, most of the dynamics is ended. Very little of it. I mean, you may say, oh, it's not 100%, but I mean, when you go about 75%, in my view, is the end of it, right? So basically, if you have 3-year horizon, just with historical averages. But then the question arises, with historical average, do I think? Bank of England used short one. They got it badly wrong. If they have used going back to 1980s and before 1970s, which we did, they got it better. But that's a choice they could have made, right? Going back to what Jagged was telling me, that the window becomes important because I can think about, do I want higher inflation or lower inflation? If I go further back, I jack up the inflation long run. I mean, I'm talking about now, not the short-term horizon. I'm talking 3 years that you say. The simple average is the answer.
Very simple.
Very simple.
And in terms of the variables, you're left with it.
Oh, no, okay, very good. I was, but I wasn't, because we did try, for example, wages, we did try all sorts of things. When you put them currently, they become important. As you put the lag of them, they just disappear. The other thing I found that when I looked at other countries, I think this argument that inflation was to do with the war in Ukraine and to do with the energy and to do with the COVID and all of this, while there are truths in them, doesn't really explain what's happening in the world inflation, in the world economy at large. Look at Brazil, look at India, and look at China inflation. Spain, just to give a European example. They are 4%, 5%. So this argument that somehow British inflation was to do with all these common factors, but then how come these other countries avoided it? So I'm just saying that's why it's important to go outside your own economy. In the interrelated world, you know, when I developed the global war, I mean, when I was given the honor degree, they did it for the global war. I said, one reporter was in Prague asked me, it's like Harikiri, this very complicated model. Why did you have to do it? You know, I said to them, the reason I had to do it because I was asked a question and I had to take it seriously. The question I was asked from a bank, I was a consultant, that what happens if there is a shock in Turkey? You know, the bank had a lot of trade, loan with Turkey. What is the effect on their bank portfolio? How would you answer that question? Because Turkey could directly trade with them or could trade with the other ones. Mercedes-Benz could be trading with Turkey and the bank is lending to Mercedes-Benz. There's so many different dimensions. I also had another conversation with the governor of the Bank of Switzerland. I was telling you, Ron, again, they wanted me to develop this model for Switzerland. He said to me, again, your model is very complicated. You know, we are a small country. We only trade with 3 nations, Germany, Italy, and France. 70% of our trade with Germany, by the way, 70% of the Swiss speak German, 20% are with France, and 10% with Italy. Why can't we just have these 3 countries in our model? I said, you can. But what do you do when you want to analyze your economy? You have to know what's going to happen to Germany, what's going to happen to France, and what's going to happen to Italy. So how do you know what's going to happen to Italy and France and Germany? You have to model them. When you model France or you model Germany, You need to understand how they relate to the rest of the world. Gradually, if you take it seriously, you have interconnected system. Right? That's the reason. Now, we can't do it because it's complicated. That doesn't mean that's logically coherent. Now, for example, when we talk about model, a structural model, how can you have a structural model of UK without having a structural model of the world economy, which interrelate to that if you want to be serious? How? How could you do it? Is UK an island still? I know we came out of Europe. Are we still thinking of island?
I think that's a fantastic place to end, actually.